Hey everyone, and welcome to another deep dive. Today we're going to be tackling something that's all around us, literally fluid mechanics.
That's right. From the air we breathe to the water we drink and everything in between, fluids are constantly shaping our world.
And to help us unravel the mysteries of this fascinating field, we have a true expert joining us.
Happy to be here.
All right, so let's jump right in. When we talk about fluid mechanics, what exactly are we talking about? What makes a fluid a fluid?
Well, think about it this way. If you try to spread cold butter on toast, what happens?
It kind of resists at first, but then it spreads out and deforms under the knife, right?
Exactly. And that's because fluids can't resist that sideways force, what we call shearing stress.
So unlike a solid, which holds its shape, a fluid will yield to pressure and take the shape of its container.
Precisely. Whether it's a liquid like water or a gas like air, anything that flows and deforms under pressure is considered a fluid.
Okay, that makes sense. Now, you mentioned density earlier, and I know it has something to do with how thick a substance is, but can you give us a more, I guess, scientific explanation?
Of course, density is essentially a measure of how much mass is packed into a given volume.
So if you have two objects the same size, but one feels heavier, it's because it has a higher density.
You got it. Think of a block of wood and a block of iron same size, but the iron feels much heavier.
Right, because it's got more mass packed into that same space.
Exactly. That means it has a higher density.
Gotcha. So density is all about how tightly the matter is crammed together.
Exactly.
Now, how does density play into how fluids behave? What role does it play in the grand scheme of things?
Well, for one thing, density plays a critical role in buoyancy.
Oh, buoyancy. That's why some things float and others sink.
Precisely. Have you ever wondered why a massive ship can float while a tiny pebble sinks?
All the time. It seems counterintuitive.
It is fascinating. It all comes down to Archimedes' principle.
Okay, and remind me what that is again.
Archimedes' principle states that the buoyant force on an object submerged in a fluid is equal to the weight of the fluid that the object displaces.
Okay, so if an object displaces a volume of water that weighs more than the object itself, it floats, right?
You're getting it. And if it displaces less, it sinks.
Like that pebble, it sinks because it displaces a volume of water that weighs less than the pebble itself.
Exactly. But a huge cargo ship, it floats because it displaces a huge amount of water, and the weight of that displaced water is greater than the weight of the ship itself.
So it's all about how much water is pushed out of the way.
You got it. And this principle is at work everywhere, from designing ships and submarines to understanding how hot air balloons work.
That's incredible. It's amazing how such a simple principle can explain something so significant.
It really is.
Now, while we're on the topic of things sinking and floating, what about pressure? How does pressure factor into the world of fluids?
Pressure is simply the force that a fluid exerts over a given area.
And the deeper you go in a fluid, the greater the pressure, right? Like when you dive deep in a swimming pool, you feel that pressure in your ears.
Exactly. That's because the weight of the water column above you is increasing, leading to more force per unit area.
Makes sense.
Yeah.
And it reminds me of how snowshoes work. By spreading your weight over a larger area, you reduce the pressure on the snow so you don't sink as much.
Perfect analogy. You've grasped the concept perfectly.
So pressure is everywhere in the world of fluids, just like density.
Absolutely. From how hydraulic systems work to the forces at play in our own circulatory system, it's a crucial concept.
This is fascinating. So far, we've covered density, buoyancy, and pressure. What other mysteries of fluid mechanics are we going to unravel today?
How about we explore something a bit more, well, slippery? Let's talk about surface tension.
Oh, surface tension. That's the force that makes water droplets beat up, right?
Exactly. It's what allows insects to seemingly walk on water.
It's like they have tiny magic shoes.
It might seem like magic, but it's all thanks to surface tension, the force that causes the surface of a liquid to behave like a stretched elastic film.
So it's like an invisible skin on the surface of the water.
You could say that. It's all because of the cohesive forces between the liquid molecules.
Cohesive forces. What does that mean?
Basically, these forces are constantly pulling the molecules towards each other, creating an inward pull at the surface.
So it's like the water molecules are holding hands, and they want to huddle together as closely as possible.
I like that analogy.
Oh.
And this inward pull creates tension, hence the term surface tension.
Makes sense. And that's why liquid drops form spherical shapes, because a sphere minimizes the surface area for a given volume.
Exactly.
So it's not just about insects walking on water then.
Not at all. Surface tension is responsible for so many things, from the shape of raindrops to the formation of soap bubbles.
This is amazing. Okay, we've covered density, buoyancy, pressure, and surface tension. What's next on our fluid mechanics adventure?
Let's delve into another fascinating property of fluids: viscosity.
Viscosity. Remind me what that is again.
Think about pouring honey versus pouring water.
Honey is much thicker and slower. Yeah.
Exactly. Honey has a higher viscosity, meaning it resists flow more than water.
So viscosity is basically a measure of a fluid's resistance to flow.
Precisely. It's all about the internal friction between fluid layers: higher viscosity, stronger friction, slower flow.
So honey has more internal friction than water
You got it.
and viscosity. It must be important for a lot of things, right? Not just pouring honey.
Absolutely. From the flow of blood in our bodies to the design of engines and pipelines, viscosity plays a crucial role.
Wow, we've covered so much already. Density, buoyancy, pressure, surface tension, and viscosity, all key to understanding how fluids behave.
It's a lot to take in, but we're just getting started.
I can't wait to see what else we uncover in this deep dive into the world of fluid mechanics.
Me too. Welcome back. Ready to keep exploring the fascinating world of fluid mechanics.
Absolutely. We've laid a good foundation, understanding things like density and buoyancy and pressure.
That's right, we've covered a lot of ground.
But where do we go from here? What other amazing properties of fluids are we going to uncover?
Well, now that we have a grasp of the basics, we can start to look at how those principles come into play when we talk about fluids at rest and fluids in motion.
Okay, so we're going from a still pond to a rushing river, so to speak.
Exactly. Fluid statics deals with fluids that aren't flowing, like a glass of water just sitting on a table.
Okay, so even though the water's not moving, it's still exerting pressure.
Yeah, got it. And one of the most important principles in fluid statics is Pascal's law.
Pascal's law, refresh my memory on that one.
Well, it states that pressure applied to a fluid that's enclosed in a container is transmitted equally throughout the entire fluid.
So like if I squeeze a bottle of shampoo, the pressure I apply at the top is transmitted all the way through the shampoo, forcing it out the bottom.
Precisely. And this principle is what makes hydraulic systems so powerful. A small force applied to a small area can generate a much larger force over a larger area.
Like those car lifts that can lift the whole car with seemingly little effort.
Exactly. Pascal's law in action.
So cool. Okay, so we've talked about fluids at rest. What about when things start moving?
That's where fluid dynamics comes in.
Fluid dynamics.
It's the study of fluids in motion. Think rivers, ocean currents, wind, even the air flowing over an airplane wing.
Things definitely get more complex when things start moving.
They do, but also much more exciting. Fluid dynamics helps us understand how weather patterns form, how blood flows in our bodies, and even how to design more efficient vehicles.
Wow, it's everywhere. So what are some of the key principles in fluid dynamics?
Well, one of the most important is Bernoulli's principle.
Bernoulli's principle. That rings a bell. Didn't we talk about that with pressure?
We did. Bernoulli's principle states that as the speed of a fluid increases, its pressure decreases.
And vice versa. So if a fluid slows down, its pressure increases.
Exactly. You're getting it. Now, let's think about how this applies to something like an airplane wing.
Okay, airplane wings always wondered how those things work.
The shape of the wing is designed so that the air flows faster over the top surface than the bottom surface.
So the air on top of the wing is moving faster, which means it has lower pressure than the air below the wing.
You got it. And that pressure difference creates an upward force called lift, which is what keeps the airplane in the air.
So the higher pressure under the wing is pushing it upwards towards the lower pressure above the wing.
Precisely.
Wow. It's crazy to think that something as simple as the speed of air can create enough force to lift a giant metal bird into the sky.
It really is remarkable. And Bernoulli's principle explains so many other things too, like why shower curtains billow inward when the water's running, or how those perfume atomizers work.
Okay, so Bernoulli's principle is all about the relationship between fluid speed and pressure.
Right.
But what about that stickiness factor we talked about earlier, viscosity? How does that play into fluid flow?
That's a great question. Viscosity plays a huge role in determining how smoothly a fluid flows.
So a fluid with high viscosity, like honey, is going to flow differently than a fluid with low viscosity, like water.
Exactly. We can think about two main types of flow: laminar flow and turbulent flow.
Laminar flow, is that like a smooth, calm river?
Perfect analogy. In laminar flow, the fluid particles move in these parallel layers, and there's not much mixing between those layers. It's smooth, orderly, and predictable.
And turbulent flow, more like whitewater rapids.
Exactly. Turbulent flow is all chaotic, unpredictable. The fluid particles are moving in random directions, creating those swirling eddies.
So the stickier the fluid, the more likely it is to flow smoothly in that laminar way.
Viscosity definitely plays a role, but the speed of the flow and the shape of the container can also influence whether the flow is laminar or turbulent.
Okay, so it's not just about the fluid itself, but also about the environment it's flowing through.
Precisely.
This is amazing stuff. But my brain needs a moment to process all this fluid dynamics is definitely a mental workout.
I hear you. It's a complex field, but we're making great progress.
Ready to tackle the final part of our deep dive. I'm excited to see where we go from here.
Let's do it.
All right, we're back and ready to wrap up our deep dive into fluid mechanics.
That's right. And so far, we've gone from the basic properties of fluids all the way to those mind-blowing principles that govern their motion.
We've learned about density, buoyancy, pressure, viscosity, even those invisible forces like surface tension,
And now we're going to zoom in even closer to the molecular level.
to the tiny particles that make up these fluids. I'm so curious to see how those little guys influence the way fluids behave.
It really is fascinating stuff. Let's go back to surface tension for a minute.
Okay, surface tension.
We've talked about how it acts like an invisible skin on the surface of a liquid, but what's actually happening at the molecular level to create this phenomenon?
Right. Those water striders aren't using magic to walk on water, so there's got to be a scientific explanation.
And there is. It all comes down to those tiny interactions between individual fluid molecules.
Interactions, what do you mean?
Well, these molecules are constantly attracting and repelling each other, creating this dynamic dance of forces.
Okay, so they're always on the move, pushing and pulling on each other. How does that create surface tension?
Imagine a molecule that's deep within the liquid.
Surrounded by other molecules.
Exactly. It's got molecules all around it, so all those forces are balanced.
Like being in the middle of a mosh pit at a concert. Everyone's bumping into each other, but there's no real direction of movement.
Perfect analogy. But now, picture a molecule that's at the surface of the liquid.
So it only has molecules below it, pulling it down.
You got it. And there are no molecules above it to counter that pull.
Ah, so those surface molecules are getting pulled inwards, like they're being tugged back towards the center of the liquid.
Precisely. And it's this inward pull that creates the tension at the surface, hence the term surface tension.
So it's like those surface molecules are holding hands, trying to minimize the amount of surface area that's exposed,
Exactly.
which explains why water droplets form those perfect little spheres.
Exactly. A sphere is the shape that minimizes surface area for a given volume. Nature always strives for efficiency.
It's amazing how it all comes back to those tiny forces between molecules.
It really is. And this interplay of molecular forces isn't just responsible for surface tension, it also explains something called capillary action.
Capillary action.
It's what allows water to defy gravity and climb up narrow tubes.
Oh, right. Like when you dip a straw in a glass of water, the water level inside the straw is higher than the water level in the glass.
You got it.
But how does it do that? How does the water climb up like that?
It's a balance between cohesion and adhesion.
Cohesion. Remind me what that is again?
Cohesion is the attraction between, like, molecules, so the water molecules are attracting each other.
And adhesion is the attraction between different types of molecules.
Right. In this case, the water molecules are attracted to the molecules of the straw.
And in this case, the adhesion is stronger than the cohesion.
Exactly. So the water is basically being pulled upwards by the straw, like it's clinging to the sides.
And the narrower the tube, the higher the water will climb.
Right, because those adhesive forces have a greater influence in a narrower space.
This is blowing my mind. All these seemingly magical properties of water are really just the result of tiny forces between molecules.
It really is amazing, isn't it? And this principle of capillary action is at work everywhere, from how plants draw water up their stems to how paper towels soak up spills.
It's like we're seeing the world with new eyes now.
That's the beauty of fluid mechanics. It's all around us, shaping our world in countless ways.
Well, I think it's safe to say we've successfully unraveled some of the mysteries of fluid mechanics today. We've explored the properties of fluids, the forces that act upon them, and even zoomed into the molecular level.
It's been quite a journey, and even though we've covered a lot of ground, we've really only scratched the surface of this incredibly vast and fascinating field.
So, to our listeners, we encourage you to keep those questions coming and never stop exploring the amazing world of science.
Thanks for joining us on this deep dive. Until next time.